Hello, everyone, and welcome to today's GoFly Master Lecture. We're very pleased that you're here to join us today, and to kick us off, I'm going to pass it over to Gwen Leiter, CEO and founder of GoFly. Gwen?
Thank you, Paul, and thank you everyone for joining us today for this incredibly exciting master lecture. As you all know by this time, GoFly's grand sponsor is Boeing, and we are joined by over 20 different organizational partners, as well as in-kind sponsors as well, to help you all design and build your personal flying devices. So without all of our sponsors and our partners, we would not have be nearly as robust or be able to offer as many benefits to all of you teams. So we are truly appreciative of all of our partners. Today, we have a phenomenal master lecture for you. We are joined today by Pete Buck, who is one of a dozen or so Lockheed Martin Senior Technical Fellows. Pete has been helping GoFly from almost its earliest inception. So thank you, Pete. We're thrilled that you're joining us. And just so you all know a little bit more about Pete, not only is he a senior technical fellow at Lockheed, but he also works at the Advanced Development Program there, which is also known as Skunk Works, since 1981. In this capacity, he has worked as a senior engineer, a project lead, and a chief engineer on many development projects ranging from very low speed to very high speed flight systems. In addition to his Lockheed Martin duties, Mr. Buck co-designed the Sonex, the Waiex, and the Xenos light sport kit aircraft, of which there are more than 600 flying examples worldwide, earning him in 2003 the August Raspet Award presented by the Experimental Aircraft Association, one of our GoFly partners, for outstanding contribution to the advancement of light aircraft. In 2010, Pete developed an all-electric powered version of the Waiex aircraft, and Pete is an active member of the ASTM, serving on both the F-37 Light Sport Aircraft Committee and the F-44 General Aviation Aircraft, and was awarded the American Society for Testing and Materials Standards Excellence Award in 2012 for his efforts in the development of electric propulsion standards. Pete is an active licensed pilot and FAA certified mechanic, and he holds a bachelor's degree in mechanical engineering from California State University, Northridge. So without further ado, Pete, we are so pleased that you are joining us, and we can't wait to hear your words of wisdom.
Thank you, Gwen. Thank you, everybody, for joining this morning. This morning in California, anyway. So let's see. I think it's my turn to jump in. We go to desktop, share screen. Okay. So again, thank you, Gwen, for introductions. What I'd like to do here today is give a perspective on development testing, some of the lessons learned I've learned through my career in development programs, trying to give some insight to those development testing and the pitfalls that one can run into. I'm going to do that through some examples relative to the electric aircraft program I, along with John Lonette and some others, have worked. So in order to do that, I need to give you just a little bit of introduction of where some of this came from and how we work through it. So there we are. Gwen kind of gave the overview, some pictures of some of my favorite airplanes up there in the upper corner. My mother sitting on the wing of our family airplane as she was flying it in the 99s, winning trophies, flying cross country. So I grew up in an aviation family and I've been in it in my entire career. Like to just spend just a moment talking about the relationship that I've had with Sonex. Sonex aircraft, John Lonette, the development of these aircraft. John Lonette contacted me, and the two of us launched the company called Sonex, where we co-designed the Sonex series of aircraft, just as Gwen had talked about, the Sonex, the Waiex, the Xenos motor glider. And then later, after we had those kit aircraft out there in the market, and we had a little bit of breathing room, we got together and said, hey, let's go do an electric aircraft and fly an all-electric aircraft. And that was in that 2006 timeframe that we jumped in and went forward with the effort. Little vision of the Eflight overview. We intended it to always be a fun sport airplane, capable of some aerobatics, something like 30 minutes of flight capability. And because there was so much development in the propulsion system and everything, we decided to do that development in a known airframe. So we used one of our Waiex airframes that we already had and converted it. Wasn't ideal. When we flew it, we had something like 40 pounds of lead in the tail to balance the airplane. But it gave us great insight, and we flew that airplane in 2010. So these development programs, and I'm sure most of you in the development that you're doing for the GoFly challenge are pretty, they really have a lot of development in them. There are things that will bite you in many, many corners as you go through the project, and you learn more as you try and bring forth a vehicle that you can actually go fly. This has a little timeline of some of the things we went through. By the time we flew the airplane, we had version 5 motor. That meant that was the 5th full up motor that we actually built, besides many changes to those motors as we went along. So 5 full motors, numerous controllers. We developed the controllers ourselves. There was no controller out there to go with the motor. So both the motor was fully developed by us, the controller fully developed. We were on like version 12 of the controller when we flew in 2010. We were able to get together with a partner on the battery system later. Philips Aerospace actually brought the lithium battery to it. We did some initial battery buildups. That turned out to be a project in itself. We did have some pretty substantial bumps in the road in trying to bring forth a battery system. We, quote, lit up many batteries in testing. They caught on fire and other fun attributes with these lithium battery systems. So a lot of lessons learned for the battery system. For the flight that we did, we were able to get Philips Aerospace to help us. But in the work with Sonex aircraft, of course, every year we had this July show, the Experimental Aircraft Association Oshkosh or Air Venture Air Show, which was one of the places that was always a main marketing for our aircraft and everything. So with such, we were always every year trying to demonstrate this electric airplane at that show. And through that time in the development, it felt like every every year we ended up into a shotgun development approach. We had, by the time we came out of the July air show, and we were all burnt out, you know, it took us a month or so to recover from that. Then we had to develop a new plan forward to have a vehicle flying at the following year's show, and it was not conducive to doing the proper development on the system through time. It wasn't thought out. It didn't have enough time in it to do the development testing to move us into a successful, a highly successful. We flew the airplane quite a bit in the 2010 and 2011 timeframe. Here's a slide of kind of some testing. It's very interesting. I've never before in my career actually tested an airplane running the motor inside a hangar. It was a very interesting testing. But of course in Wisconsin, where Sonex was located in February when it's 23 degrees below zero at that particular time, it was much better than doing it outside. But this is a picture of some of that testing. In this particular test, you can see behind the airframe there a stack of lead acid batteries that we're using for this particular testing. And you can see some test data there. And we had a motor at this point that was running at about 90% efficiency between both the motor itself and the power electronics to drive that motor. We were doing quite well from that standpoint. But we were still having temperature problems, and that's what we're going to talk about some more through this. A 54 kilowatt motor or 72 horsepower, still when you have 10% heat rejection or inefficiency that goes with that motor, that's 5.4 kilowatts of heat. That's a lot of heat to deal with. And especially when you're trying to keep the internals of a motor in a temperature range that's like 250 degrees. Internal combustion engines, you know, they'll run at max power more like 400 degrees. So you got a lot of difference or delta T between what the air is and the temperature that of the cooling fins where you're trying to dump this heat. In these electric motors, we're trying to be more in the 250 or 300 degree range max temperature for the windings. So it limits the ability to dump that heat. A couple of pictures of one of the motors. We went through many attempts. This is the version 1 motor that we have shown. We, in our full power testing, this is what that motor looked like at about 1 minute in of full power. So we scorched that one. We turned it into charcoal pretty quickly. A lot of lessons learned in this. And we went on to different versions of the motor. Version 2 motor, it was scorched, but we still have it. It's usable for tests. We still do controller testing and stuff with it, but it really can't run at very high temperatures. Version 3 motor, we completely toasted that one. It's unusable completely because of over temp. Version 4 motor, this is the version we flew in 2010. It's got a lot of flights on it. It's flyable, but it overheats. You can't maintain it at high power settings very long before it overheats. And then version 5 motor, it still has temperature or heat rejection issues with it. Not as much. We're going to go into some of that detail, but it also has some other issues. We tried to do some things for producibility that didn't work out as well as we thought they would. So as we go forward, this is where the development testing thought process comes. The motor, there's many thermal issues in these motors. When you're talking between 5 and 10% of the shaft horsepower has to be rejected in heat. In this development program, it was very difficult to understand what was causing the heat. Were we the timing or commutation or miscommutating the motor causing the heat, generating more heat in the motor for some reason? You know, the I squared R, or current squared times the resistance of the winding itself, depends on the wire gauge and its effective wire gauge. So there's the heat rejection that comes there. As you try and make these electric motors lightweight, they have lower thermal mass. So the change in temperature will happen very, very quickly. And that was indicative of our first motor where, again, in less than a minute, we destroyed the motor. And then just the fact, again, you know, 54 kilowatts of shaft output, 10% loss, that's 5,400 watts, quite a lot of heat that we still have to reject. So as we have this motor, it became difficult to understand where the problem was. There are three main areas that could be causing the problems in the motor. Transferring the heat out of the motor could be from just getting the heat from the copper winding itself into the laminations, or transferring the heat through the lamination into the fin, and then finally transferring the heat from the fin into the air. We really didn't have a sense of, through this process, of which one of these, or all of them, or a combination of all of them, was causing us the big problems. And again, in developing a brand new propulsion system, it's difficult to determine what the problem is. In many ways, any of these systems, like most of you are developing today, it's very, very complex system. There's not one attribute that's causing the problem. It's the combination of fairly complex systems. When I went back and reevaluated the analytical model that I had created for these motors, I went back and looked at those. What are the fin efficiencies I'm assuming? What are the convection coefficients and all of those things? Well, any of you who have gone through school, gone through, you know, college about heat transfer and everything, you kind of realize coming out of it that in all the textbooks and all the work you do, that the professors and the books, the textbooks always give you the convection coefficient. It's kind of given to you as the example problems or your work problems to work through. But in real life, this is a very difficult number to come up with, is what is that heat transfer between the fin itself and the cooling air. When I went through this analytical model with the number of fins I have, the thermal conductivity of the steel, I was using the steel lamination fins to transfer the laminations themselves to transfer out into the fin. The fins themselves were those lamination plates. I have a thermal conductivity to those plates and all of these analytical models. And when I run those analytical models, I come up with a heat transfer that should say everything works, but it did not match with the flight test data. So just as a testing option or a thought process that I would, from a lessons learned, I will give to you as a thought process of what should development testing be, and how do you work through these issues. So I'm going to start all the way over on the right side. If you're testing a flight-like system, that was the case that we were doing with this motor. But in a flight-like test, you capture in your testing all of the complexities of that system. These things are very complex systems. You're capturing all that complexity. When it works, you can use that as your validation test. When you develop a test, you can use that as a validation that this system works. That's the pro. The con to this is it can be very, very difficult to sort out those complex effects from those different areas of interest and the different things going on. It can be very high cost for those tests. Developing a test asset and then testing that can be very, very high cost. Of course, there's a schedule that goes with that, that very complex testing for building the hardware, building the test setup. But the most important thing that I'll say is a con that comes with testing a very, very complex system is you don't gain intuitive feel of what's going on with these problems because of all the complex nature of the test. You don't know which piece of it is causing you the problem. So if we go all the way over onto the left side, the oversimplified test. I'm just going to give it to you that if you err too far over to a simplified test, that there is no pro. You gain nothing from that test. You spend money, you spend effort doing a test, and in the end, it's oversimplified. It's not realistic compared to what your system is, and you don't gain any insight from the test, and it can even be worse. You can be led to incorrect conclusions that you then incorporate into your more flight-like system and learn once you get to your flight-like system that those conclusions were not correct. So now there's that middle ground. You know, if you can successfully define what is that focused, simplified test that is a reduced cost and schedule, it gives you the intuitive feels of what you're trying to get out of the testing that you're doing. And the test is simple, and when you test and you learn from that test, you'll have a great willingness to revise the test article and retest because it's quick schedule and it's relatively low cost, and you can conduct more tests in parallel. Meaning if you have a flight asset component that you've already built and you're now testing in parallel this test that gives you this intuitive feel, you can be doing those types of things at the same time. The con to that is it doesn't capture all the complex effects. But the biggest con is it's difficult to know when you've stepped over the line and it falls into the oversimplified test issues. You'll always be right on that ragged edge of trying to make a simple test and not be too simple. So I'm going to lead us through a little bit of that, of what we learned, or what I learned from the motor heat rejection test. So again, I think I've captured all these things that I've talked about for doing this motor testing. If I use the flight motor with all its complexity, I was unable to decipher where that heat rejection problem is coming from. I mentioned, is it from getting the heat from the windings into the steel lamination? Is it in rejecting it in heat in the fins? Is there some problem in the motor and controller? Which, oh, by the way, we were trying to work controller issues at the same time, and we were using the flight motor for working through those controller issues. That the existing motor at that time could not run at full throttle, so full heat rejection could not be demonstrated. And then the test rig would require some sort of dyno brake to absorb that shaft horsepower to be able to do a controlled test. So then I thought about, well, let's go to a motor fin simulator where I put an electric heater inside a simulator of the electric motor to dump the heat in and then test getting the heat back out. That became fairly expensive because 5,400 watts, a fair amount of heat, and I had many issues knowing, in the same vein of putting the heat into this motor simulator, it was going to be difficult. And it looked like about 6-month lead time to get the controller and all the hardware that goes with the electric heaters to do this test. So then where I went was a different motor simulator. This simulator was build a large thermal mass in the center of the motor that was represented by the windings and the magnet rotor and all that. It just needed to be a thermal mass. I could do that with just a chunk of steel that I could heat up this thermal mass. And then once I heated it up, I could put in my test rig and do a transient test to cool it off and measure the heat rejection across different temperature ranges to calibrate my models, my analytical models. So this was a fairly simple thing to do, and I set forth to do that. So this is what the test rig itself looked like. It was pretty simple. I needed a fan that represented the cooling air. That would be the flight light cooling air. You can see that, that's the green fan there. That's actually a fan that goes with like an Astro jump, one of these jump things that your kids play in. Then I had a plenum box. You can see the particle board box that's there that I could put this thermal mass fin setup inside of, and then blow the air through the fins with an exit. I had some thermocouple data. I elected not to go to a sophisticated system to gather the data. I manually recorded through time the temperatures as the part cooled down. And then down in the bottom right corner, you could see a little tube on the back of it. I had just a simple manometer gauge on it so I could tune the flow from the fan to have the right pressure, delta pressure across the cooling fins that represented what I would have in flight. I set forth down in the bottom corner, you can see one of that was actually the flight motor that we flew. But from there I had quite a number of additional lamination plates that were the cooling fin. I went off and built the thermal mass of steel plate that went in between those cooling fins and built a representative thermal mass simulator of the flight motor that you see in that bottom left corner there, that represented the motor. It had 180 laminations because that's what I had on hand. The real motor had 240, so it was quite representative, and it had all the processes of bonding the laminations together like it's done in the real motor. So that was a thermal mass of, it was 41.5 pounds of steel of thermal mass that I could then test. So here's the test results that came with that. And I gained a huge insight in this testing. The first and foremost in the table you can see is that, so again, at the beginning of time, I put this thermal mass in my oven in my kitchen. I heated it up to over 300 degrees. I brought it out into the garage, installed it into my rig, and I started my test and then recorded data manually. And this is the result of that. So the couple of things. First of all, the heat rejection coming from those cooling fins was half what I expected it to be. So I immediately knew where my problem was with this test. The second thing that came very, very insightful was I was measuring temperatures from the inlet side of the cooling air to the outlet side of the cooling air as it went across these fins and out the motor. And what I found was that the air temperature actually coming out the cooling from the cooling passage, that air temperature was higher than the winding temperature near the inlet. That told me I did not have enough airflow through the motor to actually do this job. And I had a pretty big delta from side to side on the motor. So when I plot that back into heat rejection versus lamination temperature, you can see the green line on that is my desired results from my analytical model. The red was the actual measured, a linear representation of the measured. The blue was the actual measured data that was plotted as this test rig cooled down. So understood a lot. Up in the upper corner there on the left upper corner, that's a cross section of my test rig. And what I did in that test rig is I actually opened up the cooling air inlet such that I could flow more air that didn't go directly over the fins on the inlet side and then squeeze it down tight as it got out the outlet side to try and solve my problem with the temperature from side to side that I had on the motor. About the same time, I was back doing more research on what is the thermal conductivity of the lamination steel that I was using in the motor. At the time I did my first build-ups and analytical models, I was unable to find any data. But right about that time, MIT actually published some thermal conductivity data on these motors, and on the steel material that's used for lamination. And I was able to recalibrate my model now with updated thermal conductivity numbers for these materials, along with tweaking my convection coefficient in my models, so I could now make my models match my test data. At the same time, I said, well, okay, now maybe I'll just increase the fin diameter to get more fin to make the system work better and dump more heat. When I did that, what really happened is, because the thermal conductivity of the steel was pretty low. Increase in fin length really didn't help me. The tips of the fins were running cold anyway, and making them longer just added weight and really did not substantially reject any more heat. I went through the process now armed with testing and this insight that I got from the development effort of what can I go do, and I looked at liquid cooling. Maybe that's what I want to go to. I really didn't want to go there. On the outer cuff, liquid cooling through the winding, or air cooling in a different way through these fins. Through some work, now that I had my analytical models anchored and could now do this analytical work, I came up with a process of I was to mix aluminum cooling fins with my steel laminations in this motor system. In there is a picture of what that looks like from my CAD data. I had my built up analytical models that included interfaces between the aluminum fins and the steel, which doesn't have good thermal interfaces, but I included all that in my models. I built up a process of how to go do that, and I had a model now that analytically I believe I could reject 7,200 watts of heat from this system. I went off and built that. Here's some pictures of building this stack, the cooling fins with the silicone thermally conductive silicone interface, and with my buildup of my thermal mass again with a new rig. Back into my test article. So first of all, the cooling air now, exit temperature of my cooling air is much lower than any of my laminations or fins themselves. So I have enough airflow. I increased the fin height in that system. I have more airflow through the fins. I now know, and I had the insight of having enough air flowing through. Also, the delta in temperature from side to side is now collapsed down into a much smaller number. So this test data is looking quite good. The end result from that is here are again those that plotted data. I have multiple curves in green, red, and blue on there of what is the heat rejection based on the transient the transient thermal test that I did through time. What were the temperatures, the laminations, and then how did that predict a heat rejection? What did become interesting when I had this more efficient fin system is collecting the data for this transient was tougher because it rejected so much heat that in the early part of the test, there was a large effect of getting the thing just to settle down such that it all was now a constant heat rejection through time. The other thing I was able to do from the insight I learned is I added some pitot probe and some temperature outputs for the cooling air output as well as the cooling air input. And I was able to also measure the heat rejection through the change in temperature of that cooling air times its mass flow times its specific heat for the air. And so I was able to get heat rejection now in two different mechanisms in the test. And they both were agreed very closely. I was actually amazed how close this data worked. So there's the result. And now I have a system that I'm really happy with. It will work. Here's a picture of the motor I have. This is now a 75 horsepower motor. It will maintain a 230 degree F at a full power continuous incline. This is, and the net result is, even though the motor became a little more complex in its manufacturing, I actually reduced weight by putting the aluminum fins on, and now this motor's down to 72 pounds. So coming back to testing options, this is the main thing I would ask you to look at as you go through your development testing and try and understand. The simpler you can make the test, the more insight you're going to get from that test. You can see the amount of insight that I got from mine in multiple different ways. I realized, first of all, I didn't have the proper thermal conductivity for the steel. That testing gave me the insight to go look for something to find out what's wrong with my analytical models. And also the convection coefficient obviously was not correct. And I was able to now calibrate my models. That all came from this insight in this simplified testing. In this particular case, I was able to put it right in that box of getting great insight, being able to calibrate my models, being able to validate the fix and all of those things, which I never would have been able to do if I would have continued to test the flight-like system. This simplified development testing gave me that insight. I would say lessons learned through my career is that's a difficult line to find between simplified testing and oversimplified testing, and peer reviews, talking it through with peers and everything is the mechanism to work together to try and use each other to find that line the best you can before you set forth in doing those simplified testing. Couple other examples of some stuff I've done, simplified testing. I have my throttle for my flight system. That's in the upper left there. I have a very simplified lithium battery testing rig that I've learned. I have great insight from that in that upper right picture of putting thermocouples onto the battery cells. This is a lithium ion 18650 format battery cell, just dumping the energy through resistors and getting the great insight on what the performance of those cells are and how they work, and getting the intuitive feel that is in the data that you can get for these batteries, but there's nothing like a test rig to help you. In that particular testing, when I was testing that cell that's in that picture, I was pulling 22 amps on that single lithium ion cell that you see in that upper right picture, but it's on the left side of that picture. It's incredible what those battery cells will deliver. Bottom right is a test rig for testing the position sensor that we've incorporated into the motor system that's been built. So it's a test rig for position sensing using an existing motor just to spin it. And then on the bottom left there is it was in conjunction with an intern program that I actually did with a young college person. We built a test rig for lithium batteries out of a motorcycle. So we just took this motorcycle, we analyzed and calibrated to putting an electric motor and a portion of the battery system that would go into our flight air vehicle, and built this test rig. Besides being fun to go get a hamburger or something with, it's a test rig to test the lithium battery cells. The picture that's shown there is actually with lead acid batteries in it. That was the initial testing to make sure that the test rig itself was working, and then I've tested lithium batteries in that since then. So again, just to kind of bring it back around, substantial insight to a problem can be obtained through this simple testing. Don't let yourself be pushed into a design without the appropriate development information. Now, I've been through a lot of development programs, both this that's outside of Lockheed Martin and inside of Lockheed Martin. There, across the board, will always be a push to do things with no money and no schedule. I get that, and it will happen, and it has to be balanced. But if you kick that can down the road and say, I don't need to do that development testing, you're only going to end up at a place where you have a complex flight system that you have very little insight into, and you're going to have problems, and you don't know, and you will not have the insight to work yourself through those problems. So you need to balance how much of that development testing you really do with the cost and schedule that you have. Again, the simpler the test, the more willing you are to modify it. You're going to learn with that test. That test is going to morph through time. You are going to modify it because you're going to learn something, and you're going to modify it so you learn more. And you got to leave room. It will not work the first time. You got to leave some room and expect to do other things once you get through the first round of testing, and build the things that you need to build that gives you the insight and the ability to work through that. So there's a picture, 2010, late in December, of course, in Wisconsin with snow on the ground, of our first flight of the electric airplane that we did back then. So from there, I'll move into any questions that you might want.
Great. Thanks so much, Pete. A couple of questions in already. So let's start with this one. So how soon in the process should empirical testing begin, in your opinion? Do you advocate for building and testing something pretty roughly designed quickly, or only testing after something more refined towards the end of the design process?
Wow, that's a really, really hard question. But the more basic the testing, the more insight you're going to get, and the less problems you're going to have later. So a real build-up approach is what needs to be done. If you early on, if you can just take Excel, Project, PowerPoint, Whiteboard, whatever you can, and just sit around, if you have somebody's outside of work area with a beer or something, and your peers, sketch out what are the things we can do before we commit to the design that we've got to start building, and then do development testing in parallel with building those that flight vehicle system and everything. So you can do stuff up front, and then you can do more sophisticated development testing in parallel with actually building the flight hardware. So it's going to be a mix.
Great. The Go Fly competition has a noise requirement that comes along with it. Just curious if while you were doing your development, if you did any experimenting on noise testing along the way.
I have not. Fundamentally, the electric motor itself is much quieter than the internal combustion engines, without question. But they're not quiet. When you're pulling 75 horsepower out of anything, it has an acoustic signature that goes with it, but it's not bad. For this program that we were doing, we were not chasing a low acoustic signature. We were chasing a fun sport airplane. We elected to use the same propeller at the same RPM as what we have our internal combustion engine products, because we wanted to use that knowledge base instead of making everything a new development. With that, there's a fair amount of propeller noise on our system that was not what we were doing in this program. For the noise requirements that go with a Go Fly, wow, you're gonna have to be doing some development testing to get down to those acoustic signature levels.
Great. And then if you were starting over today, are there more ready-made motor options that have the heat issue resolved that are currently available now?
I believe not. Now, of course, you see Siemens and some others who are producing motors that are high horsepower and high-end motors, that they've worked through these problems with their liquid-cooled and sophisticated systems. When you get things back into this class of vehicle that I'm talking about in the horsepower range, from a single motor, when you're in the 40 to 80 horsepower range, they're not really off-the-shelf motors or developed motors that are in that class. As you get motors down into the small horsepower range, the 2, 3, maybe 5 horsepower, these motors are available and off the shelf. And the reason is because it's a square cubed law relationship. As you get more horsepower and a bigger motor, your surface area that you have to dump the heat becomes proportionally different. So the small motors are easier to keep cool. This is why, even though some people want to claim it's for some other reasons, this is why you'll see some people go to multiple small motors, because they are available, they will work, and you combine multiple motors rather than trying to get it up into this higher horsepower range.
Great. When you were talking about the first test airplane, you talked about putting some weight in the back, in the tail. Just curious why that weight wasn't for extra batteries.
Well, with the lithium batteries, the lithium batteries in themselves are a risk item for catching on fire and everything else. We elected to keep the battery and the motor in the front and forward of the firewall, just like what we have in the internal combustion engine version of the airplane for those safety reasons. And because of that, the easiest way to do it in an existing airframe is simply put weight in the tail to get the CG to work. The firewall forward package for that internal combustion engine airplane was around 200 pounds max firewall forward for that system. For our electric version, it was about 350 pounds of weight between the battery, which was the bulk of the weight, and the motor.
Got it. And then it sounds like you did a great deal of testing along the way, and you shared a couple examples of tests, but was curious about what, if you might have a story about the most creative tests you did along the way.
Wow. It's a tough one. I'll use one that's a little off to the side, but one of the ones I am incredibly proud of here at Lockheed is on the F-117 program, stealth fighter, back in the mid 1980s. We transitioned because we had some flutter issues on the vehicle. We built new composite rudders for the airplane to solve a flutter issue at the high speeds. We were building those components out of thermoplastic composites, pretty out there in their day, and even still today. All primary structure thermoplastic composite. But these things were expensive. A rib for that structure that went inside that part, that fin, were about, in those dollars, $1980, about $30,000 a piece. I was able to convince my management to give me a small amount of development money, and when I went off and did a side program development test to show how we could incorporate injection molded thermoplastic composite components into that fin structure. And we ultimately, through that testing, that development testing, adopted that, and we reduced the cost of each of those ribs from $30,000 to well under $3,000 for each part.
Awesome. Thanks. And we're coming up on time here. So to finish off, I just wanted to ask, do you have any parting words of wisdom for the GoFly competitors you'd like to leave us with?
Parting words, wow. Development testing is important. You're going to run into the same lessons learned as many as us have in, you're going to end up putting all your eggs in one basket and then expecting it to work, and not break all those eggs. And it's probably not going to work out that way. So find the things that you can do that at least gives you a product to go into competition with that may not be everything you had hoped it to be, but is still something you can go into competition with. All of your competitors are going to be in the same boat. So none of these, in my opinion, are going to be perfect wrung out systems that have all been, all the bugs worked out of them, because the time frame doesn't allow you to do that. So all you have to do is outrun the bear, outrun the guy who's slowest. You don't have to be the fastest.
Great. Thanks, Pete.
All
with
right.
that, I'll pass it over to Gwen for some parting words.
All right. Thank you.
Pete, thank you so much for that incredibly informative master lecture. We are so appreciative that you have joined us. And to all innovators, thank you for joining us as well. We remind you that there is less than 1 week to turn in your Phase 1 submissions. They are due April 18th. We look forward to seeing all of you and to, excuse me, having you participate as well in the upcoming phases of the GoFly competition. Once again, many thanks to Pete, and good luck to all of you. Take care.
Thank you.